Okay, Rose, you can begin.
Hi, everyone, and welcome to From Astronomer to Entrepreneur, the Story of MuAnalysis, presented by EDFAS, the Electronic Device Failure Analysis Society. I'm Rose Ring, and we're glad you could join us. All participants will be in a listen mode only during the presentation. If you're having technical difficulties today, dial 877-582-7011. This will connect you with a GoToWebinar technician. We'll add your phone number into the chat in just a moment. Please feel free to submit questions at any time by using the question panel. We'll answer as many questions as we can at the end of the presentation. EDFAS is part of ASM International. ASM International is a society of professionals and students who have come together to accomplish great works for the common good which cannot be achieved independently. The Electronic Device Failure Analysis Society is a volunteer-led organization that serves the specific needs of the electronic device failure analysis community through technical resources, continuing education, and networking opportunities. EDFAS is a key part of ASM International and its overall mission. Membership benefits. Membership provides you with the resources, technical information, and connections you need to stay competitive in your field. It connects you to a professional network that will support you at each stage of your career. Membership includes a subscription to the Electronic Device Failure Analysis magazine and newsletter, online access to microelectronic failure analysis desk reference, and much more. Be sure to check out the ASM and or EDFAS websites for more details as well as for comprehensive listing of all your member benefits. You'll find a link to the EDFAS webpage in the chat. Our speaker today is Dr. Martine Simad Normandin, the president of MuAnalysis. Martine Simad Normandin founded MuAnalysis Incorporation in 2002, where she holds the position of president. Located in Ottawa, MuAnalysis is a laboratory facility offering failure analysis, material analysis, and reliability testing services to the electronics manufacturer, as well as microphotonics markets. Martine has more than 25 years experience in electronic materials analysis. Her background includes nearly 20 years at Nortel Networks, followed by 2 years at ST Microelectronics, where Martine held the position of manager, materials and device analysis in the Center for Microanalysis. Her specialties includes failure analysis and reliability testing of electronic and photonic products, detection of counterfeit electronic components, microcontamination engineering, electronic material analysis, and RoHS testing. Dr. Simad Normandin, I will turn this presentation over to you.
Hello, everyone. Thank you, Rose, for this very nice introduction. So this is going to be essentially, this is the outline of the talk. At first, I'm going to talk a little bit about MuAnalysis so you understand what kind of failure analysis company we are. Then we're going to talk about failure analysis, maybe more at a psychological or theoretical level, not getting into any particular, details of individual failure analysis, but things that are important for all of us. And then we'll get into the essentially the part of the talk, which is how did I get here? And then the lessons that I've learned about doing a startup, changes that have been happening, 16 and 23 years later, then the conclusion, and then we'll open it to question and answers. So this is MuAnalysis. I'm just going to show you a few slides from our publicity presentation. So we're private. We do electronic and photonic analysis. We're located in Ottawa, Canada. We're now 23 years old. It's a fully independent business. Over the years, we've served over 50 customers worldwide. We're registered under the control goods, so we can handle ITAR materials, and we're ISO certified. So the sort of markets we serve, essentially, there's a lot of defense and aerospace company here in Ottawa. We do a lot in lighting, automotive and transportation, semiconductors, material instrumentation, essentially pretty much anything in which there's an electronic board or device, which is just about everything nowadays. We also work with lawyers on intellectual property and trademark, and electronic manufacturing service companies, though companies who do the electronic assembly. And most of our customers are really OEMs. They have a product in which there's a lot of electronics, and when the electronics fail, it's not their expertise to find out what's going on. And we dabble in other things like textiles, and we just finished something on construction materials. So we group our services in essentially 4 groups. So materials and failure analysis, reliability testing, reverse engineering, and counterfeit detection. So in device level failure analysis, we work at the die level or the package level. Essentially, our customers experience failures in product development or qualification fallouts, or worse than that, they've sold this device and it's coming back to them as a customer return. And we work also with them in trying to figure out the wear out mechanisms. This device, as you can see, that's a gallium nitride power transistors, and as you can see, it has seen better days. We work a lot at the board level failure analysis, and there's always solderability issues. The board themselves sometimes are very, very poorly made. And, why would you put good devices on a bad board? And you're going to have all sorts of failures that, it may look like your ASIC on this board is failing, but it's really the board underneath that is failing. So, and the bad vias and interconnects. And we also do IPC inspections. So IPC 600 and 610 and a few others. If your device is good, well, we're going to do our best to try to kill it by doing reliability testing. So put it in various environmental tests, do all the JEDEC and MIL standard test. We do ESD and latch-up testing. And for military aerospace people, we do destructive physical analysis, essentially do an autopsy on a device that is still alive. In terms of reverse engineering, we work with typically law firms or the law department of a certain company, looking at intellectual property, patent infringement, trademark violations. Trademark violation, let me give you an example. Say, you bought a flashlight and it says, oh, this flashlight has a Cree lead inside. And then the flashlight, I don't know, somehow, maybe not the flashlight, maybe more a bigger luminaire, but anyway, it was involved in an accident. And now Cree is being sued because it's their LED that's inside this flashlight. And then they come to us and we prove that it is not a Cree LED inside this flashlight. It was another company. Sometimes it's very easy to identify, and sometimes it's a nameless cloning company. So this is the sort of thing we do. And we also do counterfeit detection. So, it's not only chips that are counterfeited, a lot of passive discrete, active discrete, LEDs, like I just showed you, talked about power supplies, and even cables are often counterfeit. The example on the right is quite interesting. You can see 3 tantalum capacitors who have blown up. These were essentially inside a power supply module that was inside a very high-end medical instrument. I think it was a heart-lung machine or something like this. And they were having problems, the power supply burning up all the time. When we received these capacitors, when we x-rayed them, you can see that 3 identical capacitors on their x-ray are 3 very different capacitors, and neither of them were the original, the genuine device. So that was a very interesting failure analysis we did. And we also do a lot on LEDs and luminaire analysis. So that's it for what we do. Now, why do we do it? Why do we do failure analysis? Well, it's a customer return requirement. If you make a device, we don't make any devices, but our customers do. And so if they have customer return, their reputation is at stake. If they have unexplained qualification rejects, maybe they're receiving bad part from one of their supplier and they want their money back. If it is an in-house process issue, well, they need to understand, what fix is needed so that they can improve their reliability. In the end, failure analysis is a requirement of the quality management system. Most of the ISO, essentially most ISO levels will require failure analysis. So the supply chain is a very complex thing, In an electronic device, there's a very large variety of components, including the board. The board is a component too. And so if you're a manufacturer, well, do you outsource your assembly? Most likely to Asia. Do you outsource your purchasing? So is your contract manufacturer purchasing device on your behalf? And are you sure that they're purchasing the right device? Or they're not saying, oh, we found a cheaper suppliers, and maybe you're getting counterfeits in your product. Do you purchase, complete sub-assemblies? And so the example that I just gave you of bad capacitor in a power supply sub-assembly, that is quite common. But if you're developing a product, which is a system, you're probably not going to design a power supply from scratch. You're not going to design the screen from scratch. You're going to buy all these sub-assemblies, and you may have failures in them. So in the end, you have a large number of suppliers who themselves have suppliers. And when a failure occurs, it's a hot potato. It's going around the supply chain. No one admits responsibility. And so the failure analysis lab needs to find the weak point, and very fast, because there's absolutely nothing to be gained by blaming the wrong supplier. So when we talk to our customers, we find that they do not understand the difference between failure modes and failure mechanisms, but they are not to be confused. So let's take a very simple example, an LED. It's a diode. It has 2 terminals, a cathode and an anode. It doesn't have too many failure modes. It can be dim, it can be dark, or it can be intermittent. But when it comes to the failure mechanisms, so why did it fail? There's a lot of possibilities. I mean, could be the power supply has a bad fuse, so of course your LEDs are not going to light up. You could have broken bond wires. That in itself is a failure mode because there's a reason why the bond wires broke. So you have to get to the root cause of the why. You may have poor solder joints. You could have contamination, delamination. I mean, you could get a bad die, and we've seen that. And, very, very highly dislocated gallium nitride devices, that would kill themselves. It could be a poor design in your system, not enough heat sink or transients that will essentially blow up not necessarily the LEDs, but the power, the transistor that control the LEDs. And if you have transients, you blow their gates. So if you are clear on the failure mode, then the failure analysis team can usually find the failure mechanism, usually. So failure analysis mostly is about finding the location of the problem. Once you know where the problem lies, the next steps become clear. Because remember, the root cause is not necessarily at the defect site if you can see a visible defect. The defect may be a failure mode, not the failure mechanism. An example of this I just told you is broken bond wires. Or you have a LED that looks blown, but the transistor controlling it is the one that is dead. So this is our failure analysis sequence. We like to think of failure analysis as having 3 levels: level 1, level 2, level 3. And so level 1 is essentially, understanding the problem and hopefully getting a localization of the problem. So you start with techniques that are non-destructive and non-invasive. So, a lot of photography, a lot of visual inspection, X-ray and acoustic microscopy are also non-destructive and non-invasive. Then you have to go to techniques that may be invasive but are non-destructive. So I'm thinking if you do electrical verification, you may have to solder wires to your device so you can make electrical connection. So you have changed somehow, you have invaded the device. You may have to do decapsulation to look at the die. Decapsulation, if done well, is invasive, but it is non-destructive. The device is still in the same electrical condition as when you received it. And then you do your imaging. If you're lucky, you can see a defect, and so you have localization, and that is the end of your level 1. You can write a level 1 report. If you're not lucky, the defect is hidden. There was a whole ISTFA symposium about finding the hidden defects a few years back. So all these techniques, emission microscopy, liquid crystal, thermography, they're all non-destructive, but they are all invasive in one way or another. You have to do things to your device to be able to get them to emit a signal of some sort that you can detect. So if you're lucky, you find a hidden defect, you are at level 2. You still don't know why it failed. You know where it failed. So then in the final part, in the level 3, now you do your destructive and invasive techniques where you can do delayering, cross-sectioning, materials analysis like your EDX that you do in the electron microscope, or any of these very destructive techniques. And hopefully you understand why it failed at this particular location. or why it failed and created damage at this particular location. And now you write your level 3, root cause failure analysis report. And so throughout all this, you need to keep track of absolutely everything, sample, results, everything must be numbered and kept and documented. So latch up in versus ESD, sometimes particularly to people who are not electrical engineers, they're a little bit confusing. So they are both electrical overstress, and EOS is a failure mode, not a failure mechanism. And if you go to a lab and you come back with, oh, you have an EOS, well, you've not learned anything because you've sent it to the lab because your device was dead. You know you have an EOS. So, latch up involves a power line. So latch up is an internal short that draws a lot of current. It's a very well-known failure mode of CMOS devices. And so when this short gets created, essentially the power supply will go to its maximum, setting, maximum current, maximum voltage, and whatever, and you're going to create big burn defects in your device. The power lines are typically at the top metals, and these defects are usually large and easily observable from the top of the device. ESD is an electrostatic discharge. That is p-n junction device. So these are high voltage and low current events. It's like, if you live in Canada or in the northern states, you've taken plenty of electrostatic discharge in your lifetime. So the damage that is created is at the silicon level. It's essentially the protection diodes, the ESD protection diodes that are, at the very bottom of the device, just right at the silicon level. They're typically hidden under a lot of metal layers, but they can be seen from the backside. Backside is very important in failure analysis because you immediately see essentially all the transistors and diodes of your device. The thing is that once you've blown the protection diode, the damage can cascade and blow some other transistors and things like this. And once a device is damaged, it can draw unusual current and bring devices into EOS. But the defect, if there's a visible defect, is likely to be near an IO pin and not a power pin. So they're relatively easy to separate. So not every failure analysis requires multi-million-dollar equipment. Quite often, localization of the issue is enough. So this is an example of a level 1 failure analysis. So this is an off-the-shelf component, a PNP transistor. So the customer bought this transistor from, I don't know, Mauser, DGK, or whatever, and it blew up in their product. When we looked at it, essentially we could find that it probably will be a process issue as the root cause. You can see the section of the red square is being blown up, with a plan view and a tilted view. And you can see this essentially projection of some sort of material that we never got to analyze because at this point we talked to the customer. The customer wanted to share this with the supplier, essentially the manufacturer of the PNP transistor, and then essentially we were taken away from the analysis, and we had to return this transistor to the manufacturer. And it is their problem to solve. It is not our customer to try to figure out what happened in the back in this transistor that they bought off the shelf. You know, they bought apparently a perfectly good transistor and it blew up on them. So that's, you know, an example of a level 1 failure analysis. Here's another example. This is essentially a level 3 failure analysis where we knew, I mean, you know, we were working there with a semiconductor manufacturer who had designed an ASIC. But, you know, like everywhere else, pretty much everybody else, you know, they don't have their own fab. So the ASIC was made in some fab. I don't know, don't remember which one. It could be TSMC, could be ST, could be any one of them. So they knew from their simulation that they had, well, they had some leakage and it was going to be in this particular area of the chip. So I'm showing you on the top left, you know, essentially just after delay, after decapsulation, what you're seeing the top of the device. And the second picture to the right, we have now delayered by finger polishing about 7 or 8 layers of metal, and we're now reaching the poly level. And so throughout all this, essentially, every time you delayer and remove a little bit more metal, you stop and take pictures, and you stop and take pictures. So it takes a long time. It took us about 2 weeks to get through all of this because, you know, these pictures are at low magnification. You know, once you have this picture, now you turn on the power of the microscope and you look at this area, this area, this area, trying to see if there's a tiny little defect somewhere else. Optically, we never found a defect. So on the top picture, top right picture, you see the SEM image of that particular region. And in the circle is the defect that we found. And so you see at the bottom, the two SEM images of the defect. There is a scratch on the silicon that was there right from day one when that particular wafer essentially started being processed to make these devices. Because you can see that the polysilicon is going very well over this scratch, and even the implanted regions, you know, essentially they are affected by the scratch, but because essentially the implanted region is in the scratch region. So that was a very interesting root cause failure analysis, discovering this scratch on the wafer, and it was done with very, very simple techniques. So I want to give a note to equipment manufacturers. You know, small labs like us cannot afford ultra expensive equipment because the payback time is semi-infinite. We're not working for the industry giants because they have their own labs. So our customers are small manufacturers experiencing customer returns. They have small budgets to analyze parts on which they've already have lost money. If they have a customer return, you know, they sold the part and now their customer wants their money back. So they don't have big budgets to look at this, but it's a, you know, failure analysis is a quality management requirement, and they also need to know what's going on so they can fix it. So we, the small failure analysis labs, need simple instruments, not complex systems. We want open source software. We want modular components. We want things that are easy to fix. You know, we want the circuit diagrams of what you're sending us. You know, if you don't, it doesn't matter very much in the end because we can reverse engineering it. That's what we do, but we'd rather have it. And, you know, if something is broken, just figuring out, you know, what we have to do, maybe replace a particular component on the board or something like this. Okay, so how did I get here at MuAnalysis? So, well, I studied physics at the University of Montreal. Then I went to University of Toronto to do a master's and a PhD in astronomy. So my thesis was on the large-scale structure of the magnetic field of our galaxy that I investigated through rotation measures of quasars. We did not know they were black holes back then. So in terms of fundamental science, I think this cuts, makes the grade. But then when I got this PhD, what would I do with this? I did not want to become a university professor. I had been in the education system long enough. By then, I was approaching 30 and wanted to do something else with my life. So found out that the American Physical Society had a little ad in Physics Today saying that they had scholarships for people with, well, to paraphrase, people with useless PhD to help them, transfer to industry. And I thought, well, that's me. So I applied to this postdoc, and I was lucky enough to get one. And I held it at Fairchild Camera and Instruments in Palo Alto. And so I was under the mentorship of Jim Early and John Barnes. So if you're electrical engineers or physicists, you may remember the early effect in bipolar transistor. That Jim Early. And John Barnes was very, very well known in memory at that time. So at Fairchild in the 80s, we were trying to make a 64K memory, 64K. That we had 16K back then. So after this 2 years of postdoc, I came back to Canada and settled in Ottawa. And I was hired by what was called then Bell Norton Research, but the group transferred to Norton Telecom within months. Norton Telecom at some point took the name Nortel. So that was 18 years between 82 and 99. I had various roles, and I pretty much was always associated with the silicon fab. I did a lot of process monitoring, materials monitoring, failure analysis, all sorts of things about the contamination analysis. Within these 18 years, I became what they call an intrapreneur. I made sure that the analytical services that I offered to the fab were also relevant to other groups within Nortel and to the many local startups. In the 1990s, there were lots of semiconductor startups here in Ottawa. We were called Silicon Valley North. In 2000, essentially the Nortel fab was divested to ST Microelectronics. So we went with the fab. So we were called now the Center for Microanalysis, and we supported the Silicon Fab. But we still supported other Nortel departments with materials analysis, failure analysis, reliability testing, because it was only the fab that was divested to ST to ST. The rest of Nortel still existed back then. Not for very long, but back then it still existed. And we also kept supporting the many external customers that were still around, the local startup semiconductor companies. We were a group of about 30 employees in the Center for Microanalysis. Then we were laid off. ST closed the fab, no need for analytical services. So, all the fab people plus us, plus, some other ancillary services, we were all laid off. So what to do? So I had seen the writing on the wall, and I had suspecting that the closing of the fab would happen. So I had prepared mentally for doing a management buyout. I had very strongly cultivated the external customers to the lab. So, just, out of the meeting where we were told that's it, we were on our way out, I went to the VP, announced my intention to do a management buyout, and requested some leeway to prepare a business plan. So this was essentially June 2001. So at that point, we were part of ST for exactly 1 year. So most startups go in stealth mode before launch. But we had external customers, and we could not let them think that the lab was disappearing. So we announced our plan loud and clear to the employee, to our colleagues, and to our external customers. So, between June and October, essentially I had to plan because I know the VP would be coming back, and I had to talk to essentially, finalize my plan. So the first year, as a part of ST, I had spent it learning Italian because ST is a Franco-Italian consortium, and well, French is not a problem for me, but the managers were around in meetings talking between themselves in Italian, and I had no idea what they were talking about. You could not, interject and say, "Oh, that's a good idea," or "No, how about we do it? We consider this," or whatever. So I knew nothing about corporate law, governance, finance, cash flow. So there was a book that was circulating around here by a guy called Denzel Doyce on how to start a business. I read this book over and over and over again. As I start understanding one part of the thing, then the second part started making sense. And so I had to read it many, many times over. I had a friend with an MBA, so she helped me prepare a business plan. I'd never done that before. I found an angel investor, and we prepared a term sheet to engage ST. We created a number company. So when the VP came back in October, I said, I'm ready to engage you. Here's a term sheet. I have a company. And then everything he told me in June was changed. There would be no business coming from ST. And so I had to rework the business plan. So there would be no business coming from ST. So essentially, I had to tell people that essentially it was the group of 30 people was supposed to spun out into some sort of company. Well, and continue serving ST and things like this, and doing reliability testing on their products. But that was not going to happen. So it was very hard, but I had to tell them you cannot come. Essentially, the business plan supported with no ST support, only the external customers supported 5 employees, not 30. So my colleagues were very, very mad at me at that time. But I kept telling them, you have to tell me where the revenues will come from to support your salaries. What customers will you serve? Doing what? And they expected me to find everything, all these customers overnight. I engage a corporate lawyer and a personal lawyer. So it's very important to have both, because if you're doing a startup, you have to remember that you are not the company. You need independent legal advice. So then I started negotiating to purchase the assets, found another investor, and we took the name MuAnalysis in January 2002. And we started engaging customers, on ST equipment while we were still in negotiation. So at that point, I went to see the VP. I said, it's time for me to resign. I'm in a big conflict of interest here. So hired one employee. We received our first PO And by the end of early February, we're in business. So, what have I learned? Well, the investors are essentially help you. They only care that you manage the money uh, properly. They do not help you bring business. The same goes for the directors. Your partners that have not invested will still have unrealistic expectations and will not put an ounce of work in the project. You cannot bring them in. You have to shake them and they will be mad at you. There is no perfect deal. You take the deal you can get or you get out of the race. And then you have to learn to live with that deal. Do not let lawyers take decisions or advise you. They're there to inform you, to tell you about the risks, about the laws. Lawyers are risk adverse. Entrepreneurship is a very risky endeavor, and the risks are all yours. Be prepared to work at low or no pay until the debts are under control, and that can take years. If you're wondering what to do next, when you're starting up, what is the next thing I should do? It's the thing that will bring in the money the fastest in the company. If you're thinking of doing a startup, do watch these two movies, Startup.com and Pirates of Silicon Valley. They're from the essentially the year 2000 sort of era, but it will open your eyes. And everything that's happened in those two movies has happened to me. So 16 and 12, so essentially we were acquired for the first time in 2015 and then divested again in 2022. So that was my exit strategy because you do need one. I do not own MuAnalysis anymore, but I have remained as president. I have fun, but no financial responsibilities regarding the liabilities of the company. Markets have changed. We were strictly a semiconductor company on day one. There are no more large ASIC companies around here. ATI, which was a big customer at the beginning, was acquired by AMD, and the revenues disappeared. Many others were acquired or died. This is the 2000, 2001, 2002. We nearly went bankrupt. We had to sell some of the equipment, lay off some of the staff, but we found new markets, new customers, mostly solo OEMs with supplier issues. Significant revenues for nowadays are from LEDs and power transistors. So 20 years later, things are very different. 20 years ago, we used to write our presentation and transparencies and project them on the wall with overhead projectors. I don't run to the bank to deposit checks. Everything is direct deposit or photo deposit. We no longer have a TV and a VCR. It was important for training back then, or you'd get some VHS tape and things like this. I don't have to carry a modem when I'm traveling anymore. Also, the pandemic has also changed the way we work. We hardly ever talk on the phone anymore. We meet online so we can share photos, data, etc. And everything nowadays is about web presence. We have to be on LinkedIn. I'm on ResearchGate. We have videos on YouTube. We constantly need to analyze what we do and how we do it to adjust to a changing world. My smartphone is on 24/7 because the markets are global and not everybody is in our time zone. So it's a changing and very dynamic world. what you will do in 5 years from now will be very different than what you do today. So don't be scared, just prepare. I went from astronomer to semiconductor physicist to entrepreneur. I guess my next step will be retirement. Uh, Ask for advice, but don't believe everything you're told. And ignore the naysayers. They'll always say, oh, no, you can't do this. That's not possible. Follow your dream. When a door closes, another one may just need a little push to open up. So don't be afraid to push on doors. Remember, disruptions come with opportunities. So this is all I have to say to you today. So let's open it up to the questions.
Rose, if you could unmute, please.
Oh, sorry. Thank you, Dr. Simard Normanid, for that excellent presentation. We'll now begin taking questions. Please use the questions panel to enter your questions for our speaker. We have a few questions already submitted. And the first one, in your opinion, what key challenges do you believe outsourced labs will face in the next 5 to 10 years? How do you propose to address them?
Yeah, there are essentially one of the biggest challenge is the price of instrumentation. And I mean, this challenge is here now, and it's going to get worse and worse and worse. And so it requires more and more expensive instrumentation as electronics become smaller and smaller. And it may be at some point you can't really do it. And there is a challenge of trying to dealing with silicon device level failure analysis, but those are probably going to be handled essentially by the silicon manufacturers themselves, the big foundries. But then the rest of electronics is getting smaller and smaller and smaller. Look at how dense is the electronics inside a cell phone. There's like 5 or 6 motherboards in there, all stacked on top of each other. And it's complicated to do failure analysis on those things.
Okay. Our second question. How do you manage customer expectations in terms of turnaround time?
We have to talk to them constantly and produce it's back and forth, toss up between we don't want to produce partial results, because then if you say, oh, we think it's this, it is this. And with only partial information, maybe it was your first thought, but it turns out to be wrong, and it's the wrong direction to go. But you have to keep them in the loop and tell and involve them in the process. We've done this, so a lot of online phone calls and sharing some results and things like this, at least without trying to misguide them. But we often get the thing, they're saying, oh, we've been having these problems for 6 months. How fast will you resolve it?
And our next question is, why did you choose to buy out the lab instead of finding a job elsewhere? Did you struggle to decide in your next career step?
I would have liked to stay with ST Microelectronics. I really liked the company back then. But, there are personal reasons why My husband was a high level, has a very high level job at the government of Canada. So, if we had stayed with ST, if I had stayed with ST, we would have had to move to Europe. And well, his job was not, right now, I was laid off and he was the one with a good job. So decided to stay here. And also it had been in the back of my mind, throughout the 1980s and 90s, I could see how it was going, that failure analysis was a bit of a problem. One day, when we were still Nortel, and we had a focused ion beam back then, we could afford one. Essentially, they had a problem at one spin of there was a defect on the die, and essentially we processed, I don't know how many wafers, but my team and worked with me, and we worked 24/7 for about a week, making corrections, microsurgery corrections on hundreds and hundreds of die. And then I received an email that we had saved the company so many billion of dollars by allowing the sales to be in the right quarter and not a further quarter. So I submitted my team for, this in big companies, there are always these awards and things like this. So I submitted my team and we were rejected. And essentially, they each received a telephone. And I was, blue in the face. You cannot imagine how mad I was. I went to the VP of marketing. And he told me, he said, the failure analysis lab is like the mail room. It cannot close down. It is very important to the company, but it is not part of the mainstream. And so I think that was the spark that made me think at one point I will spin this out and it will be an independent company.
Thank you for that answer. We have another one. We actually have a few, but let's take this one. Thank you. Kudos to you. What was your approach to sales and marketing? How did you find new customers? And how do you do it today? It is a very tough landscape with extreme competition.
It is so difficult to find customers in failure analysis because nobody is actively shopping for failure analysis lab. We've tried to exhibit in trade show. We find that if we exhibit at EDFAS, essentially we're exhibiting to our competitors and not to our customers. And if we try, semiconductor, other electronics trade shows and things like this, people are coming there to look at instrumentation, not to look for failure analysis laboratories. So in the beginning, essentially Nortel was still alive when we started. ATI was still alive when we started. But, as I said, as these companies disappear, we almost went bankrupt. And that's when we sort of transitioned from semiconductor to electronics. And over time now, we're more into discrete, like LEDs and power transistors. But, typically, but these failures are still more or less in systems. Nobody comes to us because they have a single LED that is dead. It's because it's died in their system. And now it's all about, as I said, it's all about being on LinkedIn, being on all sorts of platforms, YouTubes and things like this. And but it's difficult to sell failure analysis. It's like selling dentistry. You know, we have a special on root canal this week. Would you like to have one? Take advantage of it? It cannot be sold.
Thank you very much. We have another one. What's the most challenging FA request you have worked on and why?
Well, we've received a board that was essentially, you know, a piece of carbon. You know, talk about EOS. This board definitely had EOS. You know, so many burn components in there, and so essentially, it was very challenging in to try to understand where did it start? Where is ground zero of all this damage and things like this? Why it may have come about. So, but I mean, it took us a while and a lot of X-rays and removing this and removing that and electrical testing this and electrical testing that, and I think we eventually came with a plausible result. You know, there are some that you just cannot resolve, you know, with only one board and, you know, so many, you know, not that, you know, limited time and budget for it.
Thank you very much. We have, how does your lab compares to other independent labs in terms of capabilities?
Well, the thing what I see is I find that a lot of labs are subsidized, and so they have much better, more modern equipment. Our equipment is pretty old, but then, you know, because we're failure analysts, we can fix it. We can fix our equipment, but then we have also a very probably different lab. I see a lot of labs do not necessarily have FTIR, Raman spectroscopy, emission microscopy, acoustic microscopy. You know, they're mostly, a lot of them are really cross-section and SEM sort of analysis. And we do a lot of electrical and thermal imaging and, you know, things of that nature. And we were an internal lab at one point.
Yeah, okay. Hey, thank you very much. I think we don't have any more questions in here. So I would say, and people is probably still writing, we have one that says, wow, very impressive career. Thank you very much. Again, thank you, Dr. Martine Simad-Normanid, for that excellent presentation. Thank you again. Unfortunately, we don't have time to answer any more questions. We'll see, but in a few days, all participants will receive an email with further contact information.
Okay, well, thank you very much, Rose, for this opportunity.
Oh, you're welcome. So I still encourage all the folks, if you have some more questions, please connect with Dr. Normandine. And I guess all attendees, just an FYI, all attendees will receive a follow-up email when the recording has been posted, typically within 24 hours. That email will also include a participation certificate. I encourage you to please complete the brief survey that will appear on this screen as you exit the webinar. With your input, we can continue to provide webinars with high quality, practical information that you can use. Thanks again for participating in this EDFAS webinar. Have a great day, everybody. Thank you.